Gonna kill you.
The coefficient is going to be 0.
Which one?
The highest one.
The highest one. The coefficient of the highest degree can't be 0 on for any x in the interval you want to use. And all of the coefficient terms and any g of x, if it's not homogeneous, have to be continuous for all x on the interval you want to use. And actually, I'm kind of saying it backwards. All of those conditions determine intervals that you could actually use. And if you have several options for intervals that might work, the one that you pick is the one that has your IVP piece in it. It has your point from your IVP. And we've seen a few problems like that in the homework related to that idea and on the test, that last one. So we made it through the first page because I did talk about boundary value problems a little bit. So what I want you guys to do is at the very bottom of this page. Let me talk about boundary value problems a little bit. Your initial value problems, you're given a DE. Let's say I have a DE of order 2. Can somebody give me an idea of what an initial value problem? So here's the DE. You don't have to tell me the DE is order 2, so it's d squared y dx squared, or y double prime. What could be some initial conditions?
Y of 0 equals to 1.
Okay, y of 0 equals 1.
Y prime of 1 equals to 2.
Careful.
Y prime of 0.
Yes.
Y prime of 0.
Equals whatever you want. Equals 1.12 forever. Yeah.
Why?
Just because. All that matters is what distinguishes an IVP is there's an initial point. Now, we often think of 0, but it doesn't have to be 0. These just have to be at the same point because that is the initial point. Very often we think of it as t equals 0, right? No countdown. T equals 0, things happen. Yes?
Would we also get a y double prime of 0?
No, unless you have a third order. Order of 3. Because for this order of 2, you just need 2 parts.
Yeah, order 2 means how many constants will you get?
Oh, 2 constants.
2 constants, so I need 2 conditions to determine those constants. I like it. So, yes?
Does it have to be the same value in each of the levels?
For an initial value problem, yes.
So y, it has to be y of 0 and y prime of 0. It can't be some other, like 1 and 2.
No. Because the idea of boundary value problems is that you set up some interval between the 2 points you use, the 2 input points. So in this case, it's just at 0. So that is initial conditions. Doesn't have to be 0. Very often it is. It kind of jives with what we think of as initial. No time has gone by yet. Boundary value problem says, okay, I have something has to happen here, something has to happen here. Right? So then I have, like, for example, so I have a DE, order 2. So I could have y of x naught equals y naught, and y of x1 equals y. I could also involve the derivatives if I wanted to. I like it. Now this could have infinite number of solutions, no solution, one solution, any of those. You guys, everybody sort of with me here a little bit? So, try out on the first page, bottom of the page, those problems. You might need a little more room than is on there. Just to warn you. Even if I didn't say any of this, you should have enough to attack these anyway. By the way, just make sure nobody's doing something funky with the DE they give us. Does that matter to us at this point?
No.
Not a bit. They already solved it for us. We're just taking that solution and making it more specific for those conditions they give us. Solving for C1 and C2. Okay, let me check in with you guys. How's the first one going? I mean, first off, you got to be like, oh yeah, thank God, thank you, Jeff, for that shit. That's beautiful. I mean, prodigal stuff, right? So,
Yes.
y prime is going to be,
C1.
yeah, one is just leave it alone because E doesn't care.
Minus 2 sine 2x.
Oh, I like just sine 2 as well. Cool, I like it.
Part movement.
Plus C2 e to the x, sine 2x.
Plus e to x 2 cosine 2.
Plus, yeah, 2c2 e to the x cosine 2x. Good old product rule, chain rule stuff. And then you use your initial conditions. The first initial condition is, I mean, the boundary value. I forgot which one we're doing. The first boundary condition is nice. Y of 0 equals 1. So when you plug a 0 in, what happens? I mean, which piece goes to nothing?
Cosine dies.
Yeah.
Yes.
This goes away, so you just get C1 e to the 0 is C1 times 1. So you get C1 equals 1. I like it. How are we doing so far?
That's a 2x.
Where are we at? Yeah, these are all 2x's, sorry.
Yeah, I didn't realize that when I was doing it.
Ah, shit. All right. That'll throw it off a bit. All right, and then what about y prime? What does it say? Now, see, this is a boundary value problem that has, it's at like two sides of an interval, but it's on one side is talking about the value of the function, the other side is talking about the value of the slope. It doesn't matter. You can use slopes, function values. So this one says y prime at pi over 2 has to be 0. And what happens pi over 2 and the y prime? Which pieces are going to die? Well, a sign dies. So then we get C1, and this is where you might start to question yourself. Now, of course, C1 is 1, so if you want to just use that fact already. So you get 1 e to the pi over 2 times negative 1. I like it. Is that cool? Cosine of pi. That's dead, that's dead. This is not dead. So this is going to be minus for the same reason. Is that cool? C2 e to the, I left my 2 out. There you go, buddy. Pi over 2. And that's supposed to equal 0. Right? Yes. So this one is 1, this one's 0. And so here I get what? I get, so what's really nice is those go away. I can divide by negative e to the pi over 2, and I get 1 plus 2, C2 equals 0. So C2 equals negative half. So my answer is y equals. This is the part that people forget. This is just getting the answer pieces. Now you better put the answer together. So the answer is
1 for each
yeah,
of
yes. Cosine 2x minus 1/2 e to the x sine 2x. Sure. Right?
I would have said yes,
You would have said yes for what?
because it says determine whether it can be found. It didn't say it provides.
Oh, well, I'm just going ahead and doing it. Why not? Because I want to. Yeah, that's not very well worded on my end. I love it. So you're all sitting there, and you're like, how long does it take people to write the word yes?
How much more is that?
So to be honest, this isn't using a theorem or anything, because this is talking about two different inputs. So the only way to determine if it can be found is to try to find it. Right? So there's no theorem I can check the conditions of. This isn't a uniqueness kind of deal. It's two different places. I have to look for it to see if it can be found. Right? Yes?
So you just kind of attack it the same way you would an initial value?
Totally.
Okay.
Exactly. Yeah, it really isn't a different thing. It's just that the outcomes can get really interesting. While I wake this guy up, because I want to show you what this looks like, what the graph of this thing looks like. Yes?
So is the existence and uniqueness theorem only good for IVPs?
Yeah, because it talks about an interval that contains that point.
So let's say you're good if your interval is between 1 and 5, and you have like y of 2 and y prime of 3, that it doesn't necessarily guarantee it?
There's an extension to that theorem, so you can kind of feel it out that there should be. I think the way they word the theorem for us is it strictly relates to the IVP. In fact, I think it relates directly to the form for the IVP. Yeah, it talks just about the initial value problem. I don't think the book extends it to boundary value that I saw, but there is an extension for that. There is an extension. It's got a few more conditions than you might think about. It's not just good enough to say, well, there's a big enough interval that has there's a little more to it, but it's basically built off of that.
Okay.
But I don't think the book gets it all that far. Start looking at the second one if you haven't already, while I warm this dude up. Here we go.
Question. It might be kind of dumb, but like, I don't understand how IVP and BVP are. Like, I understand like in theory because you don't have the same.
All right, you ready? You ready? It is purely because those aren't the same.
Yeah, but like in practice, how would we use this as opposed to an IVP?
the most often, the most immediate place for BVPs would be like in quantum mechanics.
Okay.
You have a particle in a box, right? Which sounds like a horrible take on. Step 1, get a box. Step 2, put a particle in the box. Okay, so here. I learned that before the song came out, so we could have so much fun. So yeah, you have a particle contained between two walls, which really is like two potential.
It's an energy thing, yeah.
Yeah, so it can oscillate at so many frequencies, and you're trying to constrain it to have certain conditions at the walls,
Okay.
right? And some of those conditions could relate to what it's allowed to do there, what you want it to do, whatever, right? So that's the immediate place for a boundary value.
Okay.
Physically, you could talk about you have waves in some container, and it's sort of the same idea, just more like something you can touch. You have the walls, and you want certain things to be true at both sides. How fast do you have some frequency generator pushing, making the waves? You know, that's the thing. If the IVP has, obviously has a ton of uses, because at time 0, I need this and this and this to be true, and then you can kind of work back, and that's kinematics. You have that kind of thing going on. Initial height, initial velocity, beautiful. Initial value problem. Boundary value problem, you can actually control at several times or several physical locations.
Okay.
Yeah.
It's the range of the function.
That's right. This is a better projector, but I put on here the blue and the green. I should probably. Do you see how with the green, that's where that's the pi over 2, and that's where the slope's supposed to be 0. And then here is where I think the output's supposed to be 1, right? Looks like it. So it's not the classic quantum mechanics thing where you would see a wave function contained, because this was a slope idea on this side, right? Okay, I just want to, Desmos is stupid cool. How we doing on the second one? Anything weird coming out from there? We got one with one solution. There are 3 example problems. They probably each exhibit the 3 possible answers. So one of them is going to be one solution, we got that. Another one's going to be no solution, and another one's going to be infinite solutions. All right? Thankfully, we have the same deal up here. That's nice. And now we have this guy again, which again gives us the same thing for C1. Oh, is it y0 equals 1? So that still means C1 is 1, if I remember correctly. Yes. And now it says another kind of physical condition here.
And it's not possible because it's the same value inside the function.
So what happens when you put this in?
The same stuff cancels.
Yeah.
Yeah. So y of pi equals 0. You get C1 has to be what? If I remember. So if you put 0 in, you get you put pi in.
It has to be 0.
Yeah. C1 has to be. Now let's see. So if you put pi in, you get where am I at? C1. Oh, yeah. C1 e to the pi. Let's do this all the way up. So 0 equals C1 e to the pi times cosine of pi, 2 pi is 1. And then this piece, of course, goes away. So again, C1 has to be 0. Those two can't jive. I like it. So there's no solution there. Have you guys done the last one yet?
Yeah.
I mean, most of the work was really here, so once you do that, you're done. Now, so what's true about the last one then?
It's C1.
So the second one was no solution. Yeah, this one says y of 0 is 0, which of course is going to take care of that problem we just had. So C1 must be 0. C2, there's no condition. So C2 can be whatever the hell it wants to be.
Can we go over why the second part B didn't work again?
So for part B, it said
Why is
it said this, which leads to this. Cool?
Yeah.
Just same way, different. And then it says this, which leads to C1 having to be 0. Because it says 0 equals C1 e to the pi times 1 plus nothing. So C1 has to be 0 and 1.
Okay.
Yes.
So something can never be 0.
So there's no unique
No,
solution.
it's
That
not
does not
unique.
mean the solution does not exist.
No, it doesn't require a change. We already have what the equation is. So we
True.
don't have to do, it's not a trivial solution.
The trivial solution wouldn't work because it wouldn't go through 1. Now, look. This one, the trivial solution will work, but do you even have to consider that separately? No, because here the answer would be what? What would the answer be here? C1 is 0. That's all this tells me. So therefore, the answer is this. What could C be?
Anything.
Including 0.
0.
So you do. This does capture that trivial solution. the form of the family might not capture it always, but this one does.
And that's what it means by like infinite?
Infinite.
So- okay.
Beautiful, because you can pick whatever you want to for C2. Right? So if I plotted a bunch of these for picks of C2, they would meet both of these conditions. Of course, because sine of 0 and sine of pi are both going to be freaking 0. So in the middle, this is going to be a little more interesting. This is a little more like the quantum mechanics. Let's see if I can change this real quick. So this will be, yeah, I mean, this is one option here, but let's just make it this. So in this, well, you can have this, and then it's just going to change the amplitude, right?
Mm-hmm.
And forget anything, no. So you can have that. So it's not quite as interesting, because you can have problems where you can fit, you can fit a standing wave like this, or you can fit one like this, because it turns and comes back to be the right condition, or you can have one that go crazy. And that relates to the energy of the system, energy of the particle. Yeah,
Distance traveled, all that matters.
totally. Yes?
So when do we know when a function has infinite solutions? Is it just on the other?
You don't know going in. You know at the end.
Right.
You know when you're done, you go, oh, that anything would work here. This is what this is saying. All these conditions told me was C1 had to be 0. They have no restrictions on C2, meaning it could be anything.
Because there's no other information to find C2. Because how in the first problem, right, we could have used this to find C2 easily, but this one, what else do you do when you
Yeah,
have
the
C1?
only two conditions they gave me had nothing to do with C2 because they both killed that term. Which relates to the fact that this term meets these conditions independent of its amplitude. Right? Independent of what this is. Right? It's not the full amplitude, but I think you get the initial amplitude, whatever you call it. Does that make sense? I mean, that's what it means. Do you know going in? No, you don't. Yeah. You just work it out. I like it. And that's why you have to work it out to determine if there's going to be, what it's going to be. I like it. If you're not, like, doing your homework and at least at some point going to a computer or something to graph some of what you're getting, I don't fully understand you, to be honest. And some of you guys are like, whatever, man, I'm a mystery. But it's not always going to be like illuminating or something, but sometimes it will be, and it's just kind of nice to see what the look of it is. When you get an answer, what does it look like? I mean, it's a very fundamental part of mathematics. Is okay, this is what it looks like functionally. What the hell does it look like more physically?
What would it look like if that was 0? The number of other? I'm just curious.
Oh, it would just be a flat line, of course, yeah. And that works because it goes through those points. I like that.
I forgot that.
So that's I just keep making the amplitude, the initial amplitude smaller and smaller until it's dead. Poor little thing. Okay. All right.
So just to be
Yes.
absolutely clear, I'm sorry.
Sure.
So with N and IVP, you have whatever interval, and within that interval, it's one specific point. But with a BVP, you have like 2 points. That's your beginning and end. Okay.
Exactly. And we go in without a theorem to look ahead of time. We just have to attack it.
Mm-hmm.
Yeah. We don't have a theorem in this book. Okay. Is everybody good so far? I mean, like somebody said, it's not that different at all from IVP. It really isn't.
Or C1.
In a way, it's better. You don't have an existence uniqueness theorem that I can ask you to check. Right?
For part C.
Okay. We talked a little bit about
You can't figure it out.
homogeneous and the true meaning of that word.
You just use the first initial. First
Right? The one in
part,
chapter 2 is a very specific, localized meaning.
It gives you same point.
This one is the true general meaning in DE, is a DE equal to 0.
Especially if it cancels out the C2.
So really, if you look at it, a homogeneous DE.
Don't worry, it's not C1. It's not Y prime. Just
All right, let me see. I'm not sure how to word this without just giving it away. If I have a homogeneous DE, what will always be a solution to it? Yeah, you'll always have y equals 0 as a solution because y is in every single term. The only term that had only an x in it, g of x, is now 0. All right, beautiful. So it's always going to have that y equals 0 possibility, right? As long as any initial conditions or whatever allow that. Where am I? Oh, cool. So let's see. I did talk about the idea of
Would that be
homogeneous.
considered a trivial solution?
Yes, the trivial solution is letting y equal 0.
Okay.
Yeah. And of course, I love how the equivalent situation without a 0 is non-homogeneous. It's crazy. And now they describe this in this section, and I just want you to see what it looks like, because they are going to have examples where they use this idea. Derivatives are operators. So I can operate on an expression, and to be honest, they're linear operators. And a linear operator acts as if it's just some variable that I'm carrying through. So one basic operation that linear operators can do is they can distribute. So if I ask you, if I have 4x squared minus 3x plus sine x, and I say, take the derivative of that thing, what are you going to do? You know, you're kind of like, without even realizing it, you're going to distribute. So what this is saying is, it's like the d variable, and it just distributes. And it makes certain things we do kind of easier form to look at to do. And to be honest, remember, I don't know if you remember from the other night, we sort of teased out what we're eventually going to do when we solve a certain kind of DE. Kind of I think we actually worked it out. Then we put y equals e to the mx. Did we do that?
Yeah.
The e to the max or
And if you had like this, you could do it, Jeff. Can you? Right. If you put it like this, now watch. Here's the thing. I guess I need to tell you the whole story, but it's down there. D is y prime. D squared is y double prime. And why does it make sense that d squared? Because what is y double prime? It's an application of the differential operator twice. So this square isn't, it's valid, but it isn't like, a square. It just means I'm operating with this twice, which is exactly like matrices. If any of you guys, if you multiply something by a and multiply by a again, you can call that a squared. And it definitely isn't your regular squared, right? Matrix multiplication is its own damn thing. But it's an operator then. Matrices are operators, and the exponent just indicates how many times I've applied that operator.
So it's like the Leibniz notation with the d squared x or d.
It is directly related to it. It's directly related. And d cubed is such a, right? So you can, if I rewrote this using this notation, it would be d squared minus 3d minus 40. Now watch. This is where you got to be careful.
Brought down D.
Why? Yeah. And to be honest, that's one place I got to be careful. It actually is like D operating on Y. It really needs to operate on something. So that's my bad. I got a little too excited about. So see how this operates on Y, this operates on Y, and of course negative 40 operates on Y, makes negative 40Y. I like it. So the differential operator has to operate on something. I like it. Okay, so I can't remember if that pops up in this homework. Probably not in any crazy fashion. It's just going to pop up in this chapter. So to take this one level higher, I could call this L. So this would be Ly equals 0. This is what any homogeneous differential equation would look like. You guys see what I'm saying? And what could L be? Well, it has to be defined. You can't just put this down and say solve this. Like, what is that? Is it the first order? Is it 80th order? So it's dependent on the context, but I can rewrite it like this. It's exactly the same thing as a matrix representing a system of equations acting on several variables. You have this x plus 2y plus 3z, negative x minus 4y, and you take the matrix times the variable vector. It's the same idea. It's collecting a bunch of shit and saying it's one giant operator. Now, some of you guys might not have looked at matrices like that. I don't know. But you can, because
Maybe an hour, maybe.
again, if you take the coefficients, real quick, if you take the coefficients of my crappy thing here, and you multiply with x, y, z,
Think away.
bam, and then the next row, bam, bam, gets to the next equation, and so forth. So it just collects what the thing does into a single letter. So with matrices, what's A? Well, it depends on the problem, right? So what's L? Well, it depends on the frickin' problem. Okay, so that's in the middle of this, towards a little further down. It talks more about the linearity and the fact that we already know that derivatives have linear properties. You already know that you can, that it looks like they distribute, right? They don't really, because it's not multiplication, but they look like they do, so we call them linear operators. So that means that they're a well-behaved operator, right? Math people get all, is it linear? Yes. Oh, thank God. I could do a lot of cool shit with it. Blah, blah, blah. Okay. So I didn't want to get too deep into this, because this is just to lay the groundwork. The idea is pretty basic, but then how you use it is really nifty. It just makes it a little more focused on what we're going to do later. Yes?
Sorry, is that L of y or L times y?
L operating on y.
Gotcha.
You gotta love that shit. Yeah. So it's L operating on y. So it's sort of like me saying the square root of x equals 2. I mean, this isn't square root times x. This is square root operating on x. It's
Gotcha.
kind of a higher level way of discussing it. Since L is a combination of different things, it's differential operators and multipliers, we just say it operates on y. A more general term.
Gotcha.
Yes.
So would that be like a f sub x or something?
Come at me again with that. Huh?
Like, is that what like f sub x means?
Oh, no. F sub x is just df, dabba. Is that what you're saying?
Yeah.
Yeah. So that's just the partials.
But isn't that like operating on?
Oh, okay. Oh, I see. Okay. Not really. This is an operator notation. Because I don't have something, I would need something in front of f, right? So you could even call it the dabba x and make it an operator, but we don't do that.
Okay.
Right? You could. There's nothing wrong with it, as long as you keep it to yourself.
Yeah.
You put it in the paper, it was like, what the shit is this? Keep that in the house. All right, let me see. Okay. So again, this section is more... sure, I'll talk about it, we'll look at it, but it's more dependent on you kind of reading through it, making sure you understand, and then doing the homework. The next thing is kind of big, though, and we touched on it just a little tiny bit before. I didn't give it a proper name, but it's the principle of superposition. Doesn't mean like finding the best seat in Starbucks or something. It's
Mathematicians can name stuff.
huh?
Mathematicians, they can't
Not
name
really.
stuff.
No. Sometimes we get some stuff right. Most of the time, no. It's like those meetings, people just want to go home and they're like, sounds fine, let's go.
I feel like that's all of STEM, to be honest.
Yeah, even science, the name convention is kind of weird. The sugar plum model, what's
Have
that?
any of you guys ever heard of superposition in a
My
different...
favorite superhero.
Yeah.
Say again?
That's my favorite superhero.
Where's superposition? He's in the best place. I love that. I like it.
That should be a math t-shirt. Like that
Uh-huh.
you wear. Like, you know how you wear math t-shirts?
Superposition.
Superposition.
I don't know. I like it, though. I like it.
It's like
Have to see.
juxtaposition, except
Well, with the
not side to
logo.
side, but
Like Superman. But
All right, we'll design it. I'll make a little project. All right.
Isn't superposition like
Okay.
yeah.
superposition's like something in front of another thing?
What about constructive versus deconstructive interference?
Constructive amplifies, destructive.
Because wave functions either line up together and then they constructively interfere. So that's superposition. So it's right. If you lay a wave function out and then you put another wave function on top of it,
Yeah.
if one's like this and the other's like this, they kill each other. That's destructive interference. So that's one way. That's superposition. You're adding the wave functions together. So that's exactly what this is, to be honest, which is beautiful, because they are related. Wave functions are based on differentials. Schrodinger's equation, all that kind of business. The cat, right? No? Okay. The Rick and Morty, they're all floating around. So here, I touched on this a bit. We know that if we have a DE order 2, let me see if you guys remember. Let's say it's a homogeneous. Let's make it really, really specific. Homogeneous linear DE order 2. How many parameters? C's?
2.
2. I like it. So if I get one solution is like x, and another solution is x, natural log of x. Those are particular solutions. Those are specific values of C. Now I really want this to make sense. If I have a, as always, if I have a second order DE, just to make it really general, let me just put some of the stuff in here. Second order homogeneous DE. Get out of there. There it is. Okay. If I put something in, can you see how this is a particular solution, but inherently there's got to be a C in front of it to make it more complete? Does it have to be X for this to work? Why would putting a constant in front of it make it work? Because then the constant would be in every single term, right? And then every single term that this exists in, it would be in. And then I can just divide by it. So, of course, any constant multiple of these will work. But the principle of superposition says, if I add those together with constants in front of them, that whole thing, and we've seen that. In fact, we just did one where there was C1 blah plus C2 blah. And sometimes you do solve for one, and then you get the other one, and then you put them together with C's. And you're like, all right, I'm done. Right? So here, if you solve for that one, and then you got that one a little bit later, you can then say what's the real whole solution here. It's going to be C1x plus C2 XL and X. Become a 2. Oh.
So why is that called superposition?
Because the general idea of superposition is taking two things and just adding them together. So that I mean, really, truly, you take two wave functions, and sure, you add them together based on where they are by position. Right? So here, whatever x is, these both agree on that input. So so it kind of lines up with that idea. I'm adding any constant multiples of them. I like it, maybe. Yes, sir?
Do we have a method to create a DE knowing that the solutions are x and x natural log of x?
If you think about it, there was that bonus question where I asked you to do it, and I asked you to make it not linear. You know, I didn't have to say that. How many answers are there to that? Infinite. So just like if I said, create the equation, the Math 90 level equation that has 7 as an answer, it's like, in some sense, they're all related. They're all like, when you get to DEs, if you specify the order and you make some more constraints, then you can see the direct connection between them. But if you leave too many things open, then they really don't have to relate to each other at all. Does that make sense? I appreciate the question, but you can imagine how starting at the end and going back, you can get a lot of things. Once you set up what y prime is and what y double prime is, you can combine them in all different ways. Yeah. Now, if you want to make it homogeneous, that's an extra restriction. That makes it harder to have more than, one or two things. I like it. Okay. But, depending on the function, that's possible. Yeah. Yes?
So that last equation would be that captures all of the solutions.
Yeah, in this case, again, we don't have information about this, right. But knowing where that solution would have come from, this does follow the existence and uniqueness theorem, so that would be the unique solution. Yeah, I like it. Okay. All right. Again, some of these things are difficult to explain until we actually start solving some of these equations, seeing what could happen, right?
So can you have the superposition thingy without it being homogeneous?
Oh, of course. Yeah. In fact, I mean, spoilers, but the last thing is principle of superposition for non-homogeneous equations.
Okay.
Yeah, and which kind of only makes sense. But that's more restrictive. This one is a lot easier because that makes the damn thing 0. That makes the damn thing 0. So in some sense, it makes sense if you add them together and put them in there, it's going to make the whole damn thing 0. Right? Because, and how could I rewrite this using L?
L2.
L,
Y.
Y, equals 0. So if I plug this in, now watch, if I plug this in, L is, in fact, one reason when they picked the letter L is because it's freaking linear. So that means it does look like it distributes. See, I'm careful about how I say it. It's not really distributing, but it looks like it is. So therefore, we consider, if you ever heard of De Morgan's laws with logic stuff? So it looks like distribution, but it isn't. But we might as well just remember it like distribution. Some of you guys are like, stop talking about this shit. I have no idea. So here I could distribute this. And of course, by definition, by what the hell I just said, they each worked. So that's got to make this 0, and that's got to make this 0. So of course, it's going to be freaking 0 at the end. Okay. I like it. See, those operators made explaining that a lot quicker than using all of this shit, right? I like it. Okay. I like it. Okay, here. So, next big idea.
But once you wrote that Ly equals 0, at that point you've defined it as a second order differential equation.
Yes,
Equals
in
that
context, in the problem, L for that problem meant what I had written down.
Right, but until it's defined, it's
Then you can't use it until you have it set up and defined. Yes, exactly. So I couldn't ask you, solve Ly equals cosine x. You're like, there's no way in hell. L could be almost, it could be any freaking thing. Yes, it can do it. No, not to be evil. Okay. So real quick, example 3. I guess the next iteration of these, maybe I could put some page numbers. Verify those are solutions, and then give another solution. And I kind of gave you a hint about they're in quotes. There's no real quick way. Bless you. The verify piece isn't bad, right? It's just taking the basic polynomial stuff. The other solution would be what? Yeah, I like it. And I would actually have to accept y equals 7x cubed. Right? That is a different solution than what I wrote. Does that make sense?
Yeah.
So in terms of this problem, that would be an acceptable solution. If I said, give me the general solution for this homogeneous differential equation, you would have to say what you guys said. Y equals C1, what was it, x cubed, plus C2, x to the 4. All right, you don't get used anymore. There it is. Okay. Is that one cool? I mean, the verification step, you should be praying for those. So what do you guys know about linear independence? Independence. Okay, good. It's like banana. Linear independence. Okay, yes.
So is being free of being linear?
I like it. I like it. I curve now. I like it.
76.
I just see a line like.
Two functions can like work without depending on the other.
Okay, I like it. So,
This is not relying on one.
no. When you solve a matrix and you get 0 equals 0, or you get a line of zeros, or let me not say matrices, not everybody's working matrices. When you solve a system of equations, you get 0 equals 0. What does that mean? That system of equations is dependent. I don't know if you guys remember that word. And they didn't choose it, it just is. Linear independence means a series of functions that aren't, that one is not a linear combination of the others. Right? So for example, here's one that's dependent. Here's an example of a dependent system of equations. Like, what you got, Jeff? System, a dependent series of functions. So like x, x squared, and 2x squared minus 1. Right? Get out of there. 1. Shit. All right. Nate's like, sounds good, because I don't blame you. I just said it was. So if I call this, let me see, okay, that's good. If I call this y1, y2, y3, can you tell me, is there a way to set up a relationship between the y's that would, and you actually totally could say y1 equals some mess with this, but obviously it's easier to say, for example, y3 would be what? 2y2 minus y1. I love it. So therefore, that's why they are not linearly independent. And what that really means is that is not new information. And again, I hate to keep pointing out what kind of an advantage it is to have taken linear, but it's like that wouldn't make a complete basis set if you had three-dimensional thing. Right? Okay. Oh shit! Something else like. Say again? Yeah, but it wouldn't be able to hit all of the elements in all your three-dimensional space because it's not a basis set. They're not. So, for example, an example of like linearly independent axes are the x, y, and z axis because you can't get one as a combination of the other two by definition.
They're different planes.
If you combine any of them, you can't even get out of the freaking plane they're in, right? Is that cool? But then if I have something that's like, x, y, and then this sucker, well, that's interesting because that has a piece of the z to it, right? But obviously if I had this vector, that vector, and this vector, they are not independent. For one thing, they all lie in the same damn plane. Anyway, I just want to give you a different way to think about independence. If you can combine any two, or if you can combine any number of them to create another one in that set, they are not linearly independent. I like it. So something like this is very, very easy to see. But what happens when the functions get much more complicated? There's got to be a method. And what I always hate to do, I wanted to see if, I wanted to at least show you what the real proof looks like, but I don't think I can find it like real quick. I couldn't talk about the real proof. Maybe after we've done more of chapter 4, I can kind of give you a little handout and it would make a little more sense. The real proof why calculating the Wronskian shows you if it's linearly independent or not. So here's what the Wronskian is. And why would I write it all out? It's here. So for any given set of functions that you're curious if they are linearly independent or not, you can set up this determinant. Now, this is a great point to make sure if everybody knows how to calculate a determinant. So let's do this. Let's remind ourselves. Just want to look at a determinant by itself. So can you do a 2 by 2 determinant? And if you cannot, please do not feel like you're supposed to. Because to be honest, if you haven't taken linear, it's been at least since pre-calc that you really had to do this, if I remember correctly.
No, Calc 3 was hard
Calc
too.
3 is taught part of it.
You don't have to take Calc 3 to take this course, right? But yeah, if you took Calc 3, totally. In fact, in Calc 3, the Wronskian should show up. It should sound...
We skipped that part.
Oh.
I did.
All right. But for 2 by 2, it's easy.
Yeah.
If you just were ever told how to do it, right? So it's just
Cross
AD
minus negative 3 times
8
1.
minus
Negative
negative 3. So this will be 11.
Yeah.
And, you know, if you took linear, your brain's already going to, oh, it's invertible and blah, 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 a whole list of shit, right? Okay, and let go of that. Okay. All we need to do is be able to calculate the determinant, and then we'll figure out how to interpret what we get. What about for a larger one? I mean, real quick, by the way, just in case you're just being quiet and you have no idea what just happened, the determinant is AD minus BC for a 2 by 2. Yeah. Now for a 3 by 3. No, Jeff. There you go. You know, if I had.
What are the II thing?
Number 2 is
Oh, it's
the
number
example.
2. Sorry.
Oh, gotcha.
I use Roman numerals for. I had a student come up to me at the end of class and say, "I didn't know how you what happened." I was like, "I'm sorry, man." So who remembers how to do for this? You do have to keep in mind.
So for that
So you pick a
section
pick a column or a row. It doesn't matter. And obviously, I'm going to pick the one that's got the most zeros because that means I have to do less work. I'm not going to go through the proof for